Hello everyone, welcome to another video tutorial. Let's continue solving the problems of the chapter 2. Problem 28. 3 single phase 10 kVA 460 to 120 volts 60 Hz transformers are connected to form a 3-phase 460 to 208 volts transformer bank. The equivalent impedance of each transformer referred to the high voltage side is 1 plus J2. The equivalent resistance is 1 and the equivalent leakage reactance is 2. The transformer delivers 20 kilowatts at 0.8 power factor leading. Here we have this three-phase load. The value of the active power is 20 kilowatts. A, draw a schematic diagram showing the transformer connection. B, determine the transformer winding current. C, determine the primary voltage, and finally determine the voltage regulation. So here you can see the connection of the coils of the primary side of this three-phase transformer. Okay, we have 3 single phase transformers. We have a delta connection here and Y connection here, and here is a three-phase load. So before solving this problem, let's have a quick overview on three-phase transformers, and then we come back and solve this problem. So here in this section 2.6, we have three-phase transformers. A three-phase system is used to generate and transmit bulk electrical energy. Three-phase transformers are required to step up or step down voltages in various stages of power transmission. A three-phase transformer can be built in one of two ways: by connecting a bank of 3 single-phase transformers, or by constructing a three-phase transformer on a common magnetic structure. Okay, so in the first method we use 3 identical single-phase transformers to make a three-phase transformer, or we can construct a three-phase transformer using a common magnetic core that we will discuss that in one of the next subsections. So let's focus on the first one: bank of 3 single-phase transformers. A set of 3 similar single-phase transformers may be connected to form a three-phase transformer. The primary and secondary windings may be connected in either Y or delta configurations. So we have these 3 single phase transformers. Okay, in this figure here you can see the turns ratio N1 to N2. Right, the turns ratio is the same for these 3 transformers. So we have 3 coils for the primary and 3 coils for the secondary. We can connect these primary coils in S star or Y configuration, or in delta or triangle configuration. Therefore, we have these four possible connections: y delta, delta y, delta delta, and y y connection. We have other connections. Okay, so discussing those connections needs a separate video on three-phase transformers. So later I will record videos for three-phase transformers and we'll discuss details. Okay, but here just we have four problems for three-phase transformers, and we are going to have a quick review on three-phase transformers. That is fine for this course. So here you can see in the figure, the part B of the figure, you can see the connection, okay, in its circuit format. A more convenient way of showing this connection is illustrated in this figure, the connection that we have here. So this is the Y connection and delta connection. As you know, in the Y or A star connection, we have this star point. So we can either ground this star point or leave it as is, right? So this is also an important point, right? Considering the third harmonic. We will discuss it later. So this is the first case, y delta. The second case, delta y. The third one, delta delta. And the last one, y connection. The primary and secondary windings shown parallel to each other belong to the same single phase transformer. Yes, these three, right? And these three that are in parallel. The primary and secondary voltage and currents are shown in the figure. Also, we have these quantities here. V is line to line voltage, right? The voltage between these two lines. And this is the line current, for a star connection. For a balanced three-phase system, the phase voltage is the line voltage divided by the SQRT of 3, the square root of 3. You can review this appendix that we have for three-phase, circuits. You know this from the electric circuit theory course, but also you can review this appendix. That is good before solving these problems. Just a quick overview on equations. Yes, the power in a three-phase system: active power, reactive power, load transformations. You remember these equations, right? How we can transform a delta connection, a balanced load, to the equivalent star connection. Okay? And so on. So let's come back to our topic here. Primary and secondary voltage and currents are also shown in the figure, where V is the line-to-line voltage, A is turns ratio of the single-phase transformer, and also other possible connections that we have. So here, as you can see, we have this line-to-line voltage V. The phase voltage is V divided by the square root of 3. This is for the phase A. And this is the secondary coil of the phase A, the first single phase transformer. How much is the value of the current in it? Is A times I, turns ratio times I. In a star connection, the phase current is the same as the line current. So we have this I. And what is the value of the voltage? The phase voltage here is V, this line to line voltage, divided by the square root of 3 divided by A, turns ratio. And also you know that in a three-phase system, the line current for the delta connection is square root of 3 times the phase current, right? Similar to the equation that we have here. For a star connection, here we have these two connections. For a star connection, this is phase voltage and this is the delta connection. This is the phase current. This is the line to line voltage, V line to line. So line to line voltage is a square root of 3, a balanced three-phase system, times Vp. The line current is the same as the phase current. Okay, so this is I phase. The line current is the same as the phase current. Here we have this line to line voltage. The line to line voltage is the same as the phase voltage, right? So here we have the phase voltage, but the line current in this case, in the delta connection, is square root of 3 times the phase current. This is the important equation you remember from circuit theory course. Anyway, so you can do these calculations and find these relations between the input and output quantities for these four connections. Anyway, so here we have a quick review on these four connections and the usage of these connections when we use a Y delta connection, when we use delta Y connection, delta delta, and YY connection. Y delta. This connection is commonly used to step down a high voltage to a lower voltage. Yes, here, because we have this equation, when we have a coil that can tolerate V phase, the value of the line to line voltage will be equal to S square root of 3 times V phase. So we can have a higher line to line voltage. But if we use delta connection, the line to line voltage will be the same as this one. So here, the Y delta connection, we have right coils that can tolerate a specific value of the voltage. So in the Y case, we can tolerate a higher amount for the line to line voltage. So this connection is used to step down a high voltage to a lower voltage. The neutral point of the high voltage side can be grounded, which is desirable in most cases. Yes, we can ground the star point, this point, ground it, or leave it as is. This is also important. Delta Y connection. This connection is commonly used to step up the voltage. Okay. Delta delta. This connection has the advantage that one transformer can be removed for repair and the remaining two can continue to deliver three-phase power at reduced rating of 58% of that the original bank. This is known as open delta or V connection. Okay, we will check it in the next subsection. So in this special connection, if we remove one single phase transformer, still we can deliver the load, right? Important advantage. Y-Y connection, this connection is rarely used because of problems with exciting current and induced voltages. We will discuss that. So, the phase shift. Some of the three-phase transformer connections will result in a phase shift between the primary and the secondary line-to-line voltage. So this phase shift is shown for this case. Here for the primary, we have a star connection, and for the secondary, we have delta connection. Here we have A, B, C, also consider dot points, right? The order of dot points important. This is VAN, VBN, VCN. So suppose we have this balanced phase voltage VAN, BN, and CN. So here, what is the value of the VAB? We should write a KVL here. Okay, VAB is equal to VAN minus VBN. So this is VBN, negative VBN. If we sum up these two vectors, this is VAB. So how much, right, is the angle of VAB with respect to VAN is 30 degrees. Okay. So here, you know that if we have these three-phase voltages, this is VAN, VBN, and VCN. Okay. The negative of VBN is this one. What is this angle? Is 60. Yes, because this angle is 120. Half of it is 60. Amplitude of these vectors, right, are the same. So the summation of negative VBN with VAN is here. Okay. So this angle is 60 divided by 2, that is 30. The angle of the VBN with respect to VAN. So here in the secondary side, we have this VA, consider the dot point, VB, and VC. The summation of voltages in this loop, right, must be 0. Otherwise, we have a high circulating current inside the transformer for the delta connection. You know that. You know this concept. If we have this delta connection, okay, these three coils, dot point, right, is important. This is VA in this direction, VB, and VC. So if I write the KVL equation for this loop, we have summation of VA plus VB plus VC. Okay, we have resistances and so on. So when this summation is 0, we don't have circulating current in the delta, right, loop. But if we, for example, for the C, if we connect it in a reverse order and we have dot point here, In that case, this summation is not zero and we will have a high circulating current. So these dot points are important. And here you can see the value of the VAB, the line-to-line voltage for the secondary side is equal to VA, okay, the phase voltage. So this is VA for the secondary side, and we have VAB here, the same phasor. So what is the phase difference between the line-to-line voltage of the primary and secondary? Is 30. Okay, this is different from a single phase transformer if we consider line to line voltages. Line to line voltages are important for three phase transformers. So here you can check this point. The phasors VAN and VA are aligned, but the line voltage VAB of the primary leads the line voltage VAB of the secondary. It can be shown that delta Y connection also provides 30 degrees phase shift between the line-to-line values. Here I wrote this M file just to visualize the phase shift that we have between phase voltage and line-to-line voltage for a star connection. So here I have these three complex numbers. Amplitudes are the same, and this is VAN, the angle is 0. VBN, this is the angle, negative 2 times pi divided by 3. And this is VCN. Here just I add these phasors to plot. And also I calculated VAB, VBC, and VCA. So here you can see these three bright phasors for the phase quantities and these three red phasors for line-to-line quantities. What is the angle of the VAB? Also here I wrote a function just to display the magnitude and angle of a complex number. So here this M file is in the same current folder. Here let's use it. Display the magnitude and angle of the VAB and VAN. Okay, so if I run the code here, you can see the amplitude of the VAN is 1, its angle is 0, the angle of the VAB is 30. The line to line voltage is 30 degrees ahead of the phase voltage. What about the amplitude? Yes, the amplitude is a square root of 3 times the amplitude of the phase. So now let's solve this problem. How we can detect that this is the correct connection? Here, for the three-phase transformer, we have line-to-line voltage. The line-to-line voltage of the primary side is 460. This is the same as the voltage of single-phase transformers. So, the primary side is delta connection. Okay? Delta connection. The line-to-line voltage is the same as the phase voltage. This one. What about the secondary? For the secondary, the phase voltage is 120, but the line-to-line voltage is 208. So what is the value of square root of 3 times 120, 208. So yes, the secondary side, we have the star connection, this connection. So yes, this is the part A, and we can draw this schematic diagram considering the rated values for the phase voltage and line to line voltage that we have for this three phase transformer. Determine the transformer winding current. How we can calculate phase and line currents. So first of all, we should calculate the load current on the secondary side, I to L, this current. We have line to line voltage, and we have the active power, the power factor. So we can calculate I to L using this equation. You remember this equation from three-phase circuits, balanced three-phase circuits. The load can be in delta or Y connection, not important. Okay, so here we have these two figures from appendix. You can review the appendix. As you know, for a balanced three-phase circuit, the value of the active power of the load is 3 times V phase I phase cosine of theta. Theta is the angle between the phase current and the phase voltage. This angle. This is the same for the phase B and C also. And we know that, for example, the star connection, the phase voltage is line to line voltage divided by the square root of 3. And this is the same as this one. So we can write this equation. This is actually the same for a star or delta connection. Okay, square root of 3 line to line voltage times the line current times cosine of theta. Theta is the angle of this impedance ZA, ZB, ZC that are equal. Okay, so yes, you can review the equations. We have these equations for reactive power. Okay, either you can use again the phase values or line to line values. Anyway, so here we have this equation. The active power of the load is square root of 3 times the line to line voltage 208 times the line current times the power factor of the load. So here, if you replace the numbers, we have this value for the line current for the secondary side, 69.4. This is equal to the phase current, okay, for the secondary side. Let's check the numbers here for this problem. 69.4. This is I2. What about the I1? How we can calculate I1? We need to know the transformer turns ratio. Turns ratio for single phase, right? Quantities. So here, this is V1 phase 460, V2 phase 120. Here we have A for the phase, not to line, okay, quantities, ratio line to line quantities. So is N1 divided by N2, that is 460 divided by 120 is equal to this number. So here we can calculate I1 phase, that is equal to I2 phase divided by A is equal to 18.12. Again, how much is the value of the line current? for the primary side. Here we have delta connection. The line current is square root of 3 times the phase current. This is the value of the line current. And here, what is the number? 18.12 for the I1 phase current. Here also I calculated the ratio for the line-to-line quantities. You can see V1 line-to-line divided by V2 line-to-line is the same as I2 line divided by I1 line. This ratio for the line-to-line quantities. Anyway, let's go for the next part. Determine the primary voltage and then the voltage regulation. So here is the equivalent circuit for the transformer one phase, right? Here we have V2 prime rated one for the phase, this load, right? The power 20 kilowatt at this rated voltage 208. What is the value of the phase voltage? 120. What is the value of the V2 prime referred to the primary side rated is 460. We have this angle. For it we can consider 0 reference. This is the equivalent resistance 1, equivalent leakage reactance 2O, and here we have these two quantities, I1 phase that is equal to I2 prime phase, okay, and this is V1 for the phase. So I'm going to use this equation to calculate the voltage regulation. Here we can write, consider that this internal impedance is for the high voltage side. So because of this, I calculated quantities for the high voltage side, these quantities. And V1 for the full load condition is V2 prime phase rated plus Z equivalent times I1 full load phase. The amplitude is 18.12. What is the angle? Is 36.87. The power factor is 0.8 leading. Okay, so you know that. The value of the V1 for the full load is 454. If you replace these numbers in this equation, we can calculate the voltage regulation that is equal to negative 1.2%. This number. This is the amplitude of the voltage for the primary side. Anyway, so you can repeat this problem, okay, and redo the calculations. Let's go for the next problem. Problem 29. 3 single phase 100 kVA 2300 to 460 volts 60 Hz transformers are connected to form a 3 phase 2300 to 460 volts transformer bank. The equivalent impedance of each transformer referred to its low voltage side is this one. The transformer is connected to a 3-phase source through 3-phase feeders. The impedance of each feeder being 0.5 plus J1.5 ohm. The transformer delivers full load at the rated voltage and power factor 0.85 lagging. Draw a schematic diagram showing the transformer connection. Determine the single phase equivalent circuit. Determine the sending end voltage of the 3-phase source and finally the transformer winding currents. So here, because the line-to-line voltage of the primary side of this three-phase transformer is equal to the primary voltage of this single-phase transformer, yes, we have this delta connection for the primary side and the same again for the secondary side. The value of the line-to-line voltage is the same as the secondary voltage of this single phase transformer. So here we have this load. The transformer delivers full load. How much is the value of the load? We have 100 kVA each phase. We have three phases, so the full load is 300 kVA. This is the value of the power factor lagging. Okay, and here we have these three feeders. We have this impedance for feeder, each feeder. So this is the source line to line voltage, the line current for the secondary side. This is line to line, the rated one for the secondary. I can calculate the amplitude of the I2, right? The line current on the secondary side using this equation. The load volt ampere is square root of 3 V2 line to line times I2 line. 300 kVA is equal to this one, and the value of the current for the secondary side, the line current is 376.5 amps. So yes, this is the value of the load current that we will use it later for our calculations. Determine the single phase equivalent circuit. How we can generate the single phase equivalent circuit model of this three phase system. We should change delta connections into a star connection format. You can review again the appendix. Here also we have this section in the chapter 2, this subsection. If the three phase transformers are practically identical and the source and load are balanced, then the voltage and currents on both primary and secondary sides are balanced. The voltage and currents in one phase are the same as those in other phases, except that there is a phase displacement of 120 degrees. Okay, we know that. Therefore, analysis of one phase is sufficient to determine the variables on two sides of the transformer. A single phase equivalent circuit can be conveniently obtained if all sources, transformer windings, and load impedances are considered to be Y connected. Yes, if we change delta connections and use equivalent star connections, we can construct the Y connected model. The Y load can be obtained by the Y delta transformation. What is the Y delta transformation? You remember that from electric circuit course. If we have this delta load and if we have this impedance for the load, each branch Z delta, the value of the current IA, the line current is IAB minus ICA. That is equal to this fraction. Okay, or if you rewrite these two quantities in this format, VA minus VB minus VC minus VA, and add up, and subtract VA, we have this, or finally this one. So we have this equation. You remember that Z, right, for the Y is equal to the ZL for the delta divided by 3. These two are equivalent. You remember this equivalent transformation from the electric circuit course. Okay, so here we have this example: a star connection for the primary, delta connection for the secondary, and this delta connection for the load. So here we can change this delta connection to the equivalent Y connection. Also, this connection for the secondary coils into this one. And finally, I can generate this equivalent circuit model. You can see the value of the quantities. V is line to line voltage. The phase voltage is V divided by square root of 3. We have this turns ratio, okay, and so on. So how we can calculate, right, quantities and generate the per phase model here in this case? The value of the impedance for the secondary coil is equal to this one. For the low voltage side, we have this impedance. We can transfer it to the primary and then use the delta Y. Okay, so here we have these impedances for the secondary side of the transformer, the low voltage side. Here we have these 3 Z equivalent for the low voltage side is equal to this one, 0.045 plus J 0.16. This is the turns ratio for the single phase transformers that we have, is equal to 5. 2300 divided by 465. So what is the value of the Z equivalent for the high voltage? Is 25 times Z equivalent for the low voltage. Right here, if I write high voltage is 25 times Z equivalent for the low voltage. What are corresponding values for the star connection? We should divide this by 3. This is Z equivalent for the Y connection is equal for the high voltage side is equal to Z equivalent for the delta connection in the high voltage side divided by 3. So we will have this value for the equivalent impedance for the Y connection at the high voltage side. So this feeder, this is the source voltage, okay, in the Y connections, and this is the Z equivalent Y for the high voltage. This is the V2 rated for the Y case. The line to line voltage for the secondary side is 460 divided by square root of 3 is the phase. Then we transfer it, we refer it to the primary side. We need to divide it by 5. This turns ratio. Okay, so this is the per phase equivalence circuit of this model. Let's review. We have this feeder. We have this impedance. For the low voltage side, we transfer impedance. Then we use delta Y transformation. Also, we transfer this value of the voltage. First, we divide it by square root of 3 to have the equivalent value for the Y connection, and then transfer it. Okay, this is V2 rated for the Y connection, equivalent Y connection. In the per phase model, we should use equivalent Y connections for all delta connections. So yes, this is the equivalent per phase model. Determine the sending end voltage. How we can calculate the source voltage per phase? We can calculate it using this equation. What is the value of the current? We know the value of the line current here, I to L. This current is the same as the phase current for the equivalent Y model. Okay, so here when we use the Y model, the equivalent Y model is this one. In the equivalent Y model, the line current is the same as the phase current, and the phase voltage is equal to 460 divided by square root of 3 in the equivalent model. So we have the value of the phase current here. We can transfer it to the primary side for the phase current here. The value is equal to this one, I1. We need to use transformer turns ratio. Okay, that is equal to this one, the load current divided by 5. Yes, finally we can write a KVL here and find the source voltage using this equation. The total impedance here times the current plus V2 prime rated. Here is the value of the source voltage per phase, and line to line is a square root of 3 times this one. The amplitude is important. This is the amplitude of the line to line source voltage. So here also we have the I1 phase, okay, and I2 phase for the transformer. Yes, we have delta connections, and the connections that we have, we calculated quantities for the Y connection. So we need to divide the value of the line current by square root of 3 to have phase currents of the primary and secondary coils of single phase transformers. Anyway, you can redo the calculations and review this problem, how we derive the per phase equivalent model by these transformations, and then how we can solve and again calculate the line to line quantities. Anyway, let's go for the next problem. Problem 30. Two identical 250 kVA, 230 to 460 volts transformers are connected in open delta to supply a balanced three-phase load at the rated voltage and a power factor of 0.8 lagging. Determine A, the maximum secondary line current without overloading the transformers. B, the real power delivered by each transformer. C, the primary line currents. And finally, D, if a similar transformer is now added to complete the delta. Find the percentage increase in real power that can be supplied. Assume that the load voltage and power factor remain unchanged at 460 volt and zero point 0.8 lagging respectively. Yes, this is a special connection, right? For the delta connection, this point that we had here, this connection has advantage that one transformer can be removed for repair, and the transformer can deliver the load in V connection format. Yes, when we remove this single phase transformer, also we remove the corresponding one here, and the load can be supplied using this V connection. So in this V connection, how we can calculate the value of the power delivered to the load. Here we have this subsection in the reference. You can read that V connection. It was stated earlier that in the delta-delta connection of three single-phase transformers, one transformer can be removed, and the system can still deliver three-phase power to a three-phase load. This configuration is known as open delta or V connection. It may be employed in an emergency situation when one transformer must be removed for repair and continuity of service is required. Consider figure 20A, in which one transformer shown dotted is removed. For simplicity, the load is connected right in the Y configuration. Here, this case, we have this delta connection. We don't have the single phase transformer between the A and C terminals for the secondary and also for the primary, okay, for both sides. Here is the vector diagram, VAB, VBC, and VCA. The lines are connected to a three-phase source. We have this right phasor diagram for the primary side, line-to-line voltage. Here in this case, you can see the value of the VAB for the secondary is this one, and this is the value of the VCA, the value of the VBC, these phasors. In this case, the value of the power, the transformer windings AB and BC deliver power. This one AB and BC. We can have current in this secondary side and in this secondary side. So we can write the value of the power delivered by the AB part, this coil, is equal to this one, VAB times IA times cosine of 30 plus phi. And this is the value of the power delivered by the BC coil. Consider that this is VAB, okay, and this is IA. So we know that line-to-line voltage is 30 degrees ahead of the phase, and here we have, for example, an inductive load. So the current for the line A or for the phase A is 5 degrees behind V. So what is the value of the current? Right, this one, the current from B to C. Here you can check. These amplitudes are the same, but this is the current. This is VCA, VCN, and this is IC. The value of the current, right? Here, IC that we have. So here we don't have any current. We removed this coil. We can write this equation PBC. What is the angle between the CB and IC? Here we have CB, this voltage, and this is IC. Okay, so this angle, this one, is 30. This is 30 minus phi. Okay, 30 minus phi. And this is 30 plus phi, the angle between VAB and IA. So here we will have this summation. The power delivered by the part AB and BC is 2 VI times cosine of 30 degrees. Yes, this is the case that we have a resistive load, because we are going to calculate the maximum power delivered by the V connection here in this part of the reference. We consider the value of the phi is 0, but for inductive load or capacitive load, we should calculate the value of the phi. If we consider a resistive load, this is the maximum power delivered by the V connection. So how much is the value of the power if we have all 3 single phase transformers? Is P delta, 3 times VI. That is equal to this one, and the ratio is this one. So the power delivered by the V connection is 58% of the power delivered by the delta connection, the maximum power for this resistive load. In our case, we can replace the numbers, yes, and calculate these quantities. So first of all, how much is the maximum power if we use delta connection? Okay, if we have delta connection here and here, if we have all 3 single phase transformers, the rated power of a single phase transformer is 250 times 3 is 750. This is the power factor. So this is the maximum active power, right, that the transformer can deliver in the case of delta-delta connection. But for the V connection, what is the maximum value of the phase current? For the V connection, A, calculate maximum secondary line current without overloading. So the maximum, right, or the rated apparent power of the single phase transformer is this one, 250 kVA, is equal to the line to line voltage times the line current. This is the maximum apparent power that a single phase transformer in this connection can deliver. So the maximum current is 543. Yes. So this is the maximum current. And what is the value of the current for the primary side? We can use turns ratio transformation, or again we can use this line to line voltage. okay, times I1. That is equal to this one. This is the maximum current of the primary coil of single phase transformers. Anyway, so let's also check the numbers here for the transformers. This is the right problem 30. The maximum current for the secondary side. Also, we calculated it for the primary. What is the value of the load angle? Cosine inverse of 0.8, that is 36.87. The load is lagging. Now let's use these two equations that we have in the reference for calculation of the power delivered by the part AB and the part BC, these two. Here we need VAB, VCB, and these two, cosine of 30 plus phi, 30 minus phi. If we use these two equations, this is the phi or theta load. The value of the P1 is equal to 248.2 kilowatt. This is the power delivered by the P1, and the power delivered by P2 is 98.2. The total power delivered by the V connection is 346. How much increase we have if we use all three single phase transformers is P delta minus PV divided by PV. That is 73.2%. Let's check the numbers here. 73.2%. This is the value of the current for the primary and P1 and P2. You can check these two numbers. Okay. So yes, advantage of delta connection that it can deliver the load even if we remove one single phase transformer, okay, from the transformer bank. Okay, so before going for the next problem, let's do a few simulations in ANSYS Simplorer software to learn these concepts better. I'm going to do a few simulations considering this problem and the next one and the V connection that we discussed it here. So let's add a new simpler design. From here we can select a three-phase transformer, or we can construct a three-phase transformer using three single-phase transformers. So let's pick up three single-phase transformers like what we have in the reference. Let's investigate this property first, the phase shift. How much is the phase shift if we have a star connection here and delta connection here? So I can connect these three primary coils that we have. This is the star point. This is the line A, line B, and line C. Okay, these three lines that we have. Consider the dot points. Yes, the dot points are connected to the lines. Anyway, and now let's add three voltage sources here. Set the value of the line to line voltage equal to 100. This is sign controlled. The RMS value is 100. This is VAB, the voltage of the point A with respect to the point B. We have these three lines. This is the line A, this is the line B, and this is the line C. So, what is the VAB? Is this one. V of the line A with respect to the line B. This is VBC, and this is VCA. So we can set, right, the phases and also perform connections to create a delta source here. This is VAB, excuse me, this one. This is the voltage of the line A. I connected it here. This is the phase B, right? The second phase, the line voltage, I should connect it to this dot point. So let me copy and paste this here to have the BC and CA here. So what is this one? This is voltage of the VCA. That's right. And also we need to have VBC. So let me rotate this one. This is the point B. Here we have the line C. And this is VCA. Yes. So here I should connect this point to the B and this point to C. So here we have this delta source connected to this A star connection for the primary. Excuse me, here I should connect this point to C. Now let's set phases for the VAB. This 9 to 9 voltage, the phase is 0. For the BC, the phase negative 120. For the CA, the phase 120. And we have this connection. So according to the reference, how we can have a delta connection? Here you can see the case. This is the star and this is the delta. Okay? These lines that we have here. So if I connect this to this one, also you can check the circuit form. A, B, C. Right? A, B, then we have C, and again we connect the C to the A, and then we have the load here. So for the load, let's consider a resistive load in a star connection manner. So again, let's consider correct dot point. This is the A star point, and connect this to the phase A, this to the phase B, and this to the C. Our load is Y delta. This is Y, and we have this source. So how much is the value of the phase voltage? Let's measure it and use this electrical voltmeter, yes, to measure the voltage of the primary coil. For the first single phase transformer, here I want to measure the voltage of the primary coil, and also we can measure the voltage of the right line to line. So this is the line to line voltage here for the primary, and this is the line to line voltage for the secondary here. Voltage of this line with respect to the right this line that we have here. So now let's an AC solver 50 60 hertz, right, to run the simulation only for these two frequencies. Let's run, analyze, then we can check quantity. Simulation done. So from the data table VM3, we have it here. This is the line to line voltage, the input. So you can see the value and the angle we can check in magnitude and angle. Let's generate right report for these four values, then we can check all of them at the same time. So here show this in magnitude and angle, this in magnitude and angle, this one and this one. What is the amplitude of the VM3? VM3 is V line to line 1. Also here you can select the proper names. This is VLL for the primary. This is V phase for the primary. This is V phase for the secondary. And this is V line to line for the secondary side. Better names. Also, I did this connection wrong here. For this voltmeter, we have this line to line voltage A with respect to the B line. Okay. So now let's run the analysis and check the numbers. This is the line to line voltage 100. The angle is 0. Yes, VAB. We have this line to line voltage VAB. What about the V phase 1? V phase 1 its amplitude is 57 because the primary right side of the three-phase transformer is connected in Y configuration. What is the RMS value of the voltage? Is 100 divided by SQR T of 3. 57.7. Yes, this number. So this is the case that we have. And the transformer turns ratio is 1. We should have this number again for the line to line voltage of the secondary because here the connection is delta. So A is equal to 1. Here, as you can see for the secondary, V line to line 2, the amplitude is 57. What is the angle? Is negative 30. Okay, is in the same phase of the V2 because here we have delta connection. So this is the phase difference between the line to line voltage of the primary and the line to line voltage of the secondary. Okay. Also, you can check the turns ratio. Let's consider the turns ratio equal to 0.5. You know that this is N2 divided by N1. So here, in this case, the A is 2, right? Definitional turns ratio is different in a simple order and in this reference that we have. So if I repeat the analysis again, we can check the numbers. Here is 100 divided by SQRT3 is 57. 57, right, divided by 2, 28. So this is divided by 2, 28.8. Yes, this number. So we can do this kind of simulations and check the angles, the phase shifts between the primary and secondary. So now let's check the problems that we had. Problem 28. So here, let's copy this simpler design. I want to generate a new model, problem 28. So here we can modify the value of the parameters. So in the problem 28, we have delta connection for the primary and a star connection for the secondary. Here we should modify this. Okay, we have a star connection for the input. So let's delete these lines again. I can make this delta connection. You know the pattern. So then this is the voltage of the phase A. This is for the phase B, and this is the phase C. Here is the line-to-line voltage VAB, and this is the voltage of the phase 1. For the output, we need to have this star connection. So again, let's select and delete these lines to generate this star connection. Perfect. So here, this is for the phase A, the first phase, and this is for the B. This is for C. Here, this is the voltage of the coil, the secondary coil of the first single phase transformer, and this is the line-to-line voltage. Now set the parameters. The value of the line-to-line voltage for the input that we calculated is 454.5. So here I set this number for the amplitude. Okay, here the RMS value, here and here. Then we have this load. The active power is 20 kilowatt. The power factor is 0.8 leading. So we have a capacitive load. Okay, and here I considered this star connection. How we can have a capacitive load here? We can add this capacitor here in parallel with each branch that we have. So let's make the connections, this one, and finally this capacitor. So we should set the value of the resistance and the capacitance of these elements. We have this three-phase load. This is the value of the resistance. the capacitance that we have. Again, we have a resistance here, a capacitance, and a resistance, a capacitance here. A balanced three-phase load. The value of the active power P is equal to 20 kilowatts. So what is the phase voltage? The RMS value of the phase voltage is 120, right? The RMS value of the line-to-line voltage is 208. So for the phase, we should divide this number by the square root of 3, 120. So how much is the power loss for one resistor? We know that the power loss for the resistor is equal to V phase to the power 2 divided by the R. So R is equal to V phase to the power 2 divided by PR. PR is the power loss for one phase. That is equal to 20 divided by 3. The P phase is equal to 20 kilowatts divided by 3. Let's do this calculation. Here, 120 to the power 2 divided by 20 kilowatts divided by 3. This is the value of the resistance. Let me set this number here. The unit is ohm. This one, and this one. Okay. We can calculate the value of the capacitance in a similar way. How much is the reactive power of the capacitance? One capacitance, the reactive power QC is V phase to the power 2 divided by the reactance of the capacitor. The value of the reactance, this is Vp to the power 2 1 divided by omega c, or Vp to the power 2 times omega c. So the value of the C is the reactive power divided by V peak to the power 2 times omega. This is the value of the C. How much is the value of the reactive power? You know that here we have this triangle. This is reactive power, active, and this is S. Also, we have the power factor, this angle, the phi. The cosine of phi is 0.8. So 20 kilowatts divided by 0.8, this is the apparent power. Apparent power times, let me write this. Phi is cosine inverse of 0.8 and S for one phase is 20 kilowatts divided by 0.8 divided by 3. Okay, and what is the value of the QC? The reactive power is S phase times sine of phi. Yes, S times sine of phi is the reactive power, volt ampere reactive of the capacitor. Finally, we can calculate the value of the C. That is equal Q divided by 2 times pi times 60 times the V peak to the power 2. Excuse me, V phase to the power 2. This is the value of the capacitor in farad. And if I multiply this by 1 E3, excuse me, this by 1 E3, we can calculate it in millifarads. So let's copy this. This is millifarad. You can check the unit here. So perfect software, yes, detects units, and we can adjust numbers based on scales that we have. So yes, now this is the rated power in this case. Let's run the simulation and measure the line-to-line voltage. The value of the line-to-line voltage for the secondary must be 208 because we adjusted the input. So let's analyze and visualize the numbers. Here we have these numbers in the data table. This is the RMS value of the phase 1. Okay, this is the line-to-line voltage 1. This is correct. But for the phase 2, why we have these numbers, the line-to-line voltage is not correct. Because we didn't set the turns ratio. Okay, the turns ratio is 0.5. What was the turns ratio in our case? 460 divided by 120. So, or we can write this 120 divided by 460, n2 divided by n1 for turns ratio. So let's run again and check the numbers. Perfect software, you can do this kind of simulations, validate your numbers, or maybe you can try other combinations, okay, that we have for three-phase transformers, other combinations. In this case, as you can see, the value of the voltage is 205, but the value of the voltage that we calculated is 208. What is the reason? The reason is this. Yes, internal impedance of the transformer, we didn't consider it in our model. Okay, so let's consider this in our model and try again. So save the model. How we can consider it? This internal impedance is for the high voltage side. Okay, so I can add these elements to the high voltage side, the primary. Let me delete this, and this. So we can add this resistor and this inductor, excuse me. This is R equivalent and this is X equivalent. So this is R equivalent. The value is 1 ohm. Yes. The X equivalent, actually this is inductance and we need to modify it. We should write divide this number 2 by omega. 2 divided by 2 times pi times 60, the frequency. So here is the internal impedance of the single phase transformer that we have. So we can consider these connections. So let me check this correct. And finally, we have this one. So This is the voltage. We don't have these connections. They are added automatically. We should connect C to the A again. This one is correct. Okay. So in this case, we have added the internal impedance of single phase transformers. Let's run the simulation again to check the numbers. So here, in this case, as you can see here, we have 207.8, close to 208, just numerical roundings. Okay, anyway. So yes, it means that we did the calculations correct for the problem that we have here. Let's measure the value of the current. Here we have this current for the line. Yes, we should place the ampere meter here. I want to measure the line current for the primary and also the line current for the secondary. Consider the dot point here. This is the I of line 1, the primary. So we should place it here. Copy it. What about the secondary? We should place the ampere meter here for the line 2. So let's run the simulation again to measure the value of the line currents. In our case, the line current for the secondary is 69.4. Here, let's add a new data table, ampere meter. Where is the ampere meter? Current. Here we have IL1, IL2, not decibel. Just we need to show the value for the L1 and L2. So let's display it in magnitude and angle. 69.44, 38.3, excuse me, 31.3. Here, what was the number? 31 for the line current. Perfect. We did a counterpart simulation and generated the model in this problem in the ANSYS simple order. So maybe you can try and measure other quantities, calculate phase differences, right, is a good practice. Anyway, so what about the next problem? This one. This is similar to problem 28, not too complex. You can generate the model for delta case and also the equivalent y model and compare the results. So you can do that. Let's save the time and perform simulation for this important problem. I want to simulate this delta connection and compare. Okay, so to save the time, I created this model for problem 30. Here we have this delta connection. First, I want to simulate the full model and then we will simulate the V model. Okay, so here you can see the connections because the load is inductive. In this case, we should replace capacitors with these inductors. And now let's check the numbers. The RMS value of the voltage for the primary line to line is 230. For the secondary is 460. Okay, so I have set the value of the voltages here for these sources. Okay, and here we have these two numbers for the resistance and inductance. How we can calculate resistance? Like before. Here in this case, when we have all single phase transformers, the full power is 600 kilowatts. Per phase is 200 kilowatts. So what is the value of the phase voltage here? Here the secondary side is delta. The load is a star. Okay, the load is a star. So like before, the value of the resistance is the V phase to the power 2 divided by the power loss by the resistor. I used this equation here, this one. This is the value of the resistance. I used this number here, here, and here to get 600 kilowatts active power. What about the value of the inductance? Yes, here we have this reactive power. We can calculate reactive power per phase. And this is the phase voltage. This is X, the reactance, that is equal to omega L. So this is the value of the inductance. I implemented this equation here. The value of the power factor is 0.8. This is the apparent power per phase, right? 250. And here is the reactive power, volt ampere reactive. This is the value of the inductance in millihenries. So here is the value of the inductance, 1.24 in millihenries. If we set the numbers, okay, we have this case. Finally, we should set the transformers turns ratio is equal to 2. Yes, N2 460 divided by N1 230. So here let's run this simulation, problem 30, analyze, to check the numbers. In this case, here are value of the voltages. The line-to-line voltage for the primary 230, the line-to-line voltage for the secondary. This is the right value of the line current for the secondary, and this is for primary. If you don't want to check the 50 hertz in these tables, simply you can just select this frequency. Okay, anyway, not important. So why the value of the line current is 941 here? Yes, we calculated this current for the secondary. This is the value of the phase current when the transformer delivers the rated power. So 543.5 times SQRT of 3. 941 is the value of the line current that we have here. So everything is correct. Finally, how we can calculate the active power for this load? We can use watt meters, okay, place watt meters and measure the value of the active power and reactive power. Yes, one method is explained here in this reference in the same appendix for balanced three-phase circuits, three-phase power measurement. In this case, we use 2 watt meters. A very good reference. I highly suggest this reference. But here in ANSYS Maxwell, because we have access to the quantities directly, I implemented this equation here, Ri2 equation. This is the value of the resistance times the magnitude of R1 dot I to the power 2, the current of the resistance 1, the current of the resistance 2, and the current of the resistance 3. Okay? The value of the active power is 600 kilowatts. So we did this simulation correct. Now let's do the simulation for the V type. Okay? When we delete one transformer. So in this case, we can copy this design, paste it here. Let's rename it to problem 30 V. In this case, we should delete one transformer. Okay, so let's delete this one. If I delete this transformer, so we have this V connection. Okay, for the primary and secondary. In this case, as you can see, the value of the line current for the secondary, this ampere meter, is the value of the phase current, right? So if I run this simulation without adjusting the parameters here, what we will have, let's check. In this case, we will have these voltages, okay, like before, and this current the same as before, but this current 941 is higher than the rated current of the secondary coil of single phase transformer. Here in this case, this current is the current of the transformer, right? And in this problem, we should find the maximum, right, line current without overloading. Here in this case, we are overloading the transformer. So we have to reduce the value of the current to keep it equal to the rated one. How we can do that? We can use numbers that we calculated here. In the V case, this is the total power delivered to the load, the active power. So I can use this number. So let's check. Here, this is equal to 346.4 E3 divided by 3, right? This is the full power. We need the value per phase. This is the value of the new resistance to set the value of the current equal to the rated one. So, okay. What about the value of the inductance? This is the phi. This is the apparent power. I should use this. This is the active power per phase divided by 0.8. This is the apparent power per phase. And this is the reactive power. So what is the value of the inductance in millihenries? Is this one. So let's set the numbers. Then we can check. Again, if I run this simulation, we can check the value of the line current. In this case, the value of the line current is 543. Yes, we did calculations correct. And now this current is equal to the rated one. We didn't overload the transformer. Here is the amount of the active power. I need to modify this equation, right? We should use the new value of the resistance. Yes, this is the new value of the resistance. So if I change this number, this is the active power, 340, right? 6 kilowatts, the same number that we have here. Perfect software. We can do these simulations. And as you can see here, in V case, only using 2 transformers, we can deliver a 3-phase load. Even you can measure the value of the P1 and P2 separately. How we can do that? The P1 is the power delivered by this transformer, and the P2 is power delivered by this one. You can use watt meters and measure the power. So let's check the first one. Here I deleted this, right, measurement tools, and I want to add this watt meter just to check. Here is the power delivered by this transformer P1. So we need its voltage and its current. This is its current and this is the voltage. Let's analyze and check the value of the power. So wattmeter 1, what is the value of the active power? The real component is equal to 98 for 60 hertz case. Again, if you don't want to see 50 hertz, only you can select this one, 98.1. Okay, 98. So yes, this transformer, you should check connections, not important, right? The order. Okay, so you can add up a new wattmeter and measure the value of the power delivered by this single phase transformer and compare the number. A good practice, you can do that yourself. Yes, the time of this video is high. Let's continue in the next video.